When people think of architectural marvels, Africa is rarely the first place that comes to mind. Yet the continent boasts structures whose engineering sophistication, precision, and durability continue to inspire modern architects and engineers. Among the most studied are Great Zimbabwe in southern Africa and the rock-hewn churches of Lalibela in Ethiopia. These sites were constructed centuries ago without modern tools, yet they demonstrate mastery of structural logic, material science, and urban planning. Far from legends or myths, the achievements of these builders reflect applied engineering and innovative problem-solving, showing that African societies were centers of architectural knowledge long before colonial accounts reshaped the narrative. Great Zimbabwe, engineering without mortar. Constructed between the 11th and 15th centuries, Great Zimbabwe was the political and economic capital of the Kingdom of Zimbabwe. The city spans over 700 hectares, featuring massive stone enclosures, circular towers, and complex pathways. Modern engineers study the site because of the ingenious dry stone masonry, a technique that achieves stability without mortar. Dry stone masonry. At Great Zimbabwe, granite blocks were precisely cut and fitted so that friction and gravity alone hold the walls together. The precision is remarkable. Stones interlock tightly, even in curved walls, allowing the structures to withstand centuries of environmental stress. Key engineering principles include tapered stone placement. Stones were slightly wider at the base and narrower at the top, creating stability through gravity and weight distribution. Curved walls. Many walls are slightly curved, distributing lateral forces and preventing buckling. Circular towers, such as the iconic Great Enclosure Tower, functioned as both defensive and symbolic structures while applying these principles. Interlocking patterns. Engineers today note that the stone arrangement absorbs environmental stress, including wind, rain, and minor seismic activity. Urban planning and structural logic. Great Zimbabwe is not just a collection of stone walls. It was a carefully planned urban center. Key features include zoning. The city was divided into elite areas, commoner settlements, and storage facilities, reflecting both social hierarchy and functional planning. Drainage systems. Channels and terracing directed rainfall away from structures, reducing erosion and foundation damage. Material efficiency. Builders quarried granite locally and shaped stones for maximum interlocking efficiency, reducing labor while enhancing stability. Modern engineers examine Great Zimbabwe to understand how durable large-scale structures can be built without cement or steel, and how structural form can integrate with function and urban design. Lessons for modern engineering. Great Zimbabwe demonstrates principles that remain relevant today. 1. Gravity-based stability. Effective use of weight distribution can reduce reliance on binding materials. 2. Curved geometry for strength. Circular and curved walls increase lateral strength and stability. 3. Integration of function and form. Structures serve social, political, and defensive purposes simultaneously. 4. Sustainable material use. Locally sourced stone ensures longevity while minimizing environmental impact. These lessons inspire modern sustainable architecture and earthquake-resistant construction techniques. Lalibela. Engineering in monolithic stone. Thousands of kilometers to the north, the rock-hewn churches of Lalibela, 12th to 13th centuries, showcase a different but equally sophisticated engineering approach. These monolithic churches were carved directly from volcanic tuff, creating freestanding structures integrated into the surrounding rock. Precision carving. Lalibela's builders remove rock from the top down, sculpting entire churches, roofs, walls, and interior columns from a single stone block. Mistakes in carving could compromise the entire structure, yet the churches remain stable today. Engineering insights include load distribution. The monolithic design ensures that weight is evenly transferred from roof to ground, eliminating weak joints common in multi-piece construction. Structural columns. Interior pillars are carved from the same rock, providing vertical support while maintaining material continuity. Seismic resilience. Engineers studying Lalibela note that rock joints and carving patterns allow the structures to flex slightly during seismic activity, increasing stability. Urban layout and functional design. The churches of Lalibela are connected by trenches, tunnels, and courtyards, reflecting advanced planning for access and circulation. Tunnels and walkways ensure smooth movement of people and ceremonial processions. Engineering principles illustrated. Both Great Zimbabwe and Lalibela illustrate key engineering principles. 1. Material mastery. Builders understood the properties of stone, granite in Zimbabwe, tough in Lalibela, and leveraged its strengths for stability and durability. 2. Structural logic. Both sites distribute loads efficiently, absorb environmental stresses, and maintain balance across large structures. 3. Environmental adaptation. Drainage, stone selection, and building orientation minimize damage from weather, erosion, and seismic activity. 4. Labor and project management. Constructing these sites required careful coordination of labor, resource allocation, and planning. Ancient civil engineering at its finest. Enduring lessons for modern engineering. The architectural marvels of Africa, from Great Zimbabwe to the rock-hewn churches of Lalibela, are far more than historical curiosities. They are blueprints of ingenuity, sustainability, and resilience that modern engineers can learn from. The principles behind their construction remain relevant in today's world, particularly as contemporary architecture increasingly values environmental responsibility, structural efficiency, and context-sensitive design. 1. Sustainability, harnessing local materials. One of the most striking lessons from African architecture is the use of locally sourced materials. At Great Zimbabwe, builders relied on granite quarried within a few kilometers of the site. Similarly, Lalibela's churches were carved directly from volcanic tuff native to the surrounding mountains. Using local materials offered several advantages. Reduced environmental impact. Transporting heavy stones over long distances requires energy and infrastructure. By sourcing materials nearby, ancient builders minimized environmental disruption and labor costs. Modern engineers can draw lessons from this approach by emphasizing site-specific materials, low-carbon construction, and resource efficiency, all of which are central to sustainable architecture today. 2. Durability through design, engineering without modern technology. African builders achieved remarkable structural stability without cement, steel, or cranes, relying instead on precision, geometry, and natural forces. Precision placement. In Great Zimbabwe, stones were shaped and positioned to interlock perfectly, ensuring that walls remained stable even without mortar. The slight tapering of walls, from wide bases to narrower tops, distributed weight efficiently and prevented collapse. Load distribution. Both Great Zimbabwe and Lalibela demonstrate careful attention to weight management. In Lalibela, monolithic construction allowed the entire roof, walls, and floors to act as a single load-bearing system, distributing forces evenly and reducing stress points. Geometry and structural logic. Curved walls, circular towers, and interior pillars were not only aesthetic choices, but structural solutions that enhanced resilience against environmental stress, such as wind, rain, and minor seismic activity. The principle is clear. Durability is often less about material innovation and more about smart design. Modern engineers can apply these lessons in low-tech, low-cost contexts, particularly in developing regions where local conditions demand resourceful, resilient construction methods. 3. Integration with society, architecture as social infrastructure. African architecture was deeply integrated with social, political, and ceremonial life. Buildings were functional, symbolic, and socially meaningful, an aspect often overlooked in contemporary architecture. Social hierarchy. Great Zimbabwe's enclosures clearly demarcated spaces for rulers, elites, and commoners, reflecting an understanding of social organization. The placement of walls, towers, and courtyards guided movement, activity, and authority, ensuring functional governance through design. For modern engineers and architects, this highlights the importance of contextual and human-centered design. Buildings should serve communities, respect social norms, and integrate with local environmental and cultural conditions. Engage with history. If you were inspired by the engineering genius of Great Zimbabwe and Lalibela, subscribe for more stories uncovering Africa's scientific, and architectural achievements. Leave a comment below. What construction method or engineering insight surprised you the most? Let's explore Africa's innovation together.